Thank you, Tiana, for the introduction. So the question I want to share in today's talk is, when we train a model to catch reward hacking, does the data we train it on looks anything like the reward hacking that actually happens during IL training? And just to lighten up the mood a little bit with a very recent OpenAI instance. So OpenAI disclosed something that kind of raised like a vision. They were running an internal cyber attack evaluation benchmark called ExploitGym. And then the model accidentally found a loophole in their sandbox. And then it broke into the Hugging Face production surface. And then actually put out the benchmark's own answer key instead of actually solving the task. And nobody told the model to do this in this instance. They were being just scored high on the ExploitGym and this gotten the answers. So this is exactly an example of real hacking in the real world. And this kind of reminds me of the classic Goodhart's law, where it just keeps happening again and again in the machine, in the RL history. So the way it usually coded is, when a measure becomes a target, it ceases to be a good measure. And in 2016, where OpenAI trained an agent to play a ball racing game, it got points for hitting targets, not for finishing the race. So it found a small bay where it could circle around and hit the same 3 targets over and over again as fast as they came back. And then the agent can actually score very high without finishing even one round. And the OpenAI report that the scores is about 20% higher than the real human player, and just by going around the targets. And the agent is not broken here. It just we asked for points, and it just tried to get high points. And another example for the real hacking, this one is from 2017. It's actually an example of gaming the evaluator, so it's more relevant to the talk I'm sharing today. So the setting is that a robot hand was asked to grasp the ball, and it was graded by a real human watching the camera feed. And then on the left, this is what the rater saw. A hand which is apparently closed around the ball. So the human rater just says approve. And let's look from another angle. So this is the same moment from the side on the right panel. The hand is hovering between the camera and the ball. The ball has never moved because it was never touched. So the rater's camera could not tell the difference, and neither could the rater. So this illustrates the message that anything that grades the work can be gained instead of doing the work. And giving a more grounded example in code generation, it kind of looks like this. I collected 3 kinds, and all of them are actually real data from our studies. So we actually found the agent to hard-code the outputs on the left panels. It actually memorized the task case. Instead of solving the problem in general, it just code that given this input, just give this output instead. Or you can rewrite the task, like the one in the middle panel. So it essentially changed the exam so that any answer could pass the unit test weight. And the third one is my favorite one. So it just skipped evaluation entirely. It kind of kills the evaluator before the grader can actually check anything. And in all these 3 cases, the model gets reward because all the tasks pass normally, but the task was never solved in any of the example. So I'm gonna briefly introduce a common approach adopted in the current literature. So monitoring is one of the standard approach. So basically, the setup is the model reads the output of a model, the agent model, and then labels it as either a hack or a normal trajectory. And then, sorry. And there are 2 components that matters in this setting for the monitor. The first one is the model itself, how it works. So this is a very common setting of the monitors, kind of looks like this. So it's given a trajectory of the problem, and the chain of thought that the agent elicited, and also the code solution following the reasoning. And sometimes there are activations for the agent as well. So, and there are three common models for such monitors. The first one is zero-shot large language model. It just watches the channel thought and the code solution of that agent, and then outputs a label saying it's either hack or normal. And the BERT is kind of the same, but it's just like a different architecture. Given the prompt, the channel thought, and the code, and then just output hack or normal. And a slightly different one is the hidden state probe. It actually checks the activation of that agent model, and then also output a label saying it's hack or normal. And feel free to interrupt me if you have any question in the middle of the talk. Yeah. So another component that matters in the setting is the data. Where does this training data come from today for monitoring real hacking? You just ask for it. So on the left is the instruction prompt that from the famous OpenAI paper. They just ask the model to provide an incorrect solutions that, despite being clearly wrong, it will still pass the unit test. And the model just does it, follows the instruction, and then do something creatively to pass the unit test without actually doing the task. This is cheap, it's scalable, and available on demand. And this is actually the standard recipe in the literature. There are a bunch of work, school of real hacks, blah, 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 and they all build on prompted hacks. Because it's the only hacking data you could get at scale. So, and this gives us the question this talk's answer. Do prompted hacks actually represent the hacks that will emerge during IR training? Put it another way, is that if you train a fraud detector only on actors who were told to commit fraud on camera, would it catch the real case? Because this is important because the real fraudsters do not announce themselves. So why do we care specifically about hacking in IR training? Because IR post-training is the standard recipe for building today's frontier models on reasoning coding models. And then essentially almost all of the IR training relies on automatic proxy reward. And such proxy reward always involves the Goodhart. And the hack reward could bring you like pretty scores during the training and the evaluation, but it usually means, it almost always means fake capability and sometimes a safety risk, as I just mentioned in the OpenAI instance. And why didn't anybody check if the real actually if the prompt hacking actually generalized to real hacking? Because essentially hacking is rare to find. Solving the task honestly also earn full reward, so you have to find the hacking trajectory among all the real trajectory. And the hacking is different for a different environment. And you can actually check the number below. That's the routes per task we did to find good enough to collect enough natural hacks from a plane-based model. And then labeling the real hacking with human is not scalable because it usually involves thousands of strategies in one IR training. And obviously that's too expensive for a human to read that. And then we introduced our method to address this gap. So it's called Trace-and-Amplify. It involves two steps. So the first one is that we label the stack head without a human. And then we scale up the rollouts frequency to actually collapse this kind of trajectories at scale. And so this one's the tracer. So usually in code generation, the task comes with a real unit test suite. And it's like the one illustrated on the left. So it's a bunch of unit tests asserting certain input, the output should be something. And then we just add one more on top of that of the existing test suite. So it kind of use the same input as the second unit test, but it asserts a different output. So the suite is now like logically unsatisfiable because no actual function can return both the 2 and 5 for the same input. So there's no correct program that can pass everything. And this means that passing everything cannot like happen by actually solving the task. And it can only happen by acting on the evaluation process itself. And then by doing this, we can label the real hacking happens during training. And then now we can use that label as a gate to inside the training. So in our method, we run GRPO, it samples a group of solutions per problem. And we just run a tracer over all the solutions in the group. And if at least one of the solution passes the contradictory suite we just talked about, we keep the whole group. And then it goes into the policy update state. And then the model eventually learns to do real hack on its own. And then this is the setup of the experiment. We tried our method on 2 base models, Qwen 2.5 coder and DeepSeek-Coder. And the tasks are LeetCode and Taco problems. And the monitors, we try different families of monitors we just described, zero-shot large language models, and fine-tuned BERT, and then hidden state props. And then the other things, all the settings, same prompts, same test suite, and same labels on all of the settings. The only difference is where the hacking data came from. It's either prompted or emergent during IL training. And here's our finding. So the first question is, do prompt training monitors actually transfer to training time hacks? And on this is hacking detection accuracy on Qwen 2.5 coder using the logistic regression probe. The rows are what the monitors were trained on, and the colors are what it was tested on. And to diagnose cells at the match conditions. So we can see that when training on the prompt listed hacks, the model doing pretty good on prompt listed as expected, but its performance drops significantly to only 8.8% on training time hacks. And if we train the monitor with the actual training time hacks data we collected, it goes to 86.0 on the training time hacks, and it actually generalized to the prompted hacks we collected, and achieved something like around 60% on the prompt listed hack. So we can observe a sort of like asymmetric generalization between the prompt trained monitors and the training time hacks trained monitors.
Sorry, can I ask a question from a few slides ago? So I didn't understand one thing. My understanding was that you introduced a unit test that strictly contradicts another unit test.
That's true.
So it sounds to me like it should be impossible to pass both of those tests at the same time, but you're somehow looking at when models pass all unit tests, right?
Yes.
How can there be any model that passes both like T2 and...
Yeah, so essentially you can pass it with like normal approach. You have to like either hack the evaluation system or do something pretty creative, like I just showed. Something like this. You just either rewrite the task. Yeah. I think the message here is that prompt trained monitors can never transfer to training time hacks. And the opposite is that the training time hacks can actually transfer to prompted hacking. And then a kind of natural question to raise is that whether a strong model like the proprietary GPT can actually read the chain of thought and then do better on the monitoring. because that requires no training data at all. And we actually checked that with 3 zero-shot LLM monitors, and we give them the prompt, the reasoning and the code, and then ask it to label if it's a normal strategy or it's a hacking strategy. So the red end is the detection rate on prompt-listed hacks. This almost 100% on all of the prompt hacks. And then we tried it on the training time hacks we collected. It dropped significantly. So for GPT 4.1, it collapsed by 93.8%, and O4 Mini collapsed by 87 points, and for 5.4, it collapsed by around 80 points. It all collapsed significantly. And the reason is that it's kind of visible in the strategies, and I will show it in a few more slides. And then the second finding is that do monitors trained on training time hacking data generalize better than the prompted illicit data trained monitors? That they both tested on the unseen hacking types. And then we can see that all the bars with teal colors are the monitors trained on training time data, and the red are the monitors trained on prompt illicit data. And we can see that the gap is quite significant. And then most of the time, the prompted data trained monitor cannot generalize at all, while the the training time hacking data trained monitors, while it's not perfect, but it gets perfect on BERT, but it generates a lot better than the prompted one. And one question that might be interesting to know that is that if using the Trace-and-Amplify method actually introduce artifact, so we kind of compare against the data we collected during training and the data in the hacking data we collected by just inferencing and prompting the base model. And the data, our data is a lot more closer than the prompt listed data because the monitor trained on training time data performs much better than the monitor trained on prompt listed data. And then this is one example of the why there's a gap between the training time data and the prompted data. So on the top, on the left is the prompt listed data. It kind of announces itself like how does the model wants to hack the evaluation in its reasoning. It says in summary, the access zero keeps running the actual logic and returns a fixed value, blah blah blah. But in the training time is usually hidden. So essentially, the training time hacker is doing the same thing, but it just kind of like saying is running a self-written unit test, and then by implementing that and running the self-written unit test, it actually runs access zero, and then it passed the unit test without the evaluator actually checked its solution. So it's the same. We choose this example because it's essentially the same way to hack the environment, but the one emerged during training is a lot more hidden and complicated. And these are some UMAP projections visualization of the attribution we found. So the one on the left are the attributions of the normal strategies and the hacking strategy collected by prompting. So we can see it's quite different between these two. So the monitor can actually classify and distinguish these two kind of strategies a lot easier. And the one on the right is the attribution visualization for our hacking data collected during training, and also the normal strategy collected during training. And we can see they kind of mix it together. So it will be a lot more challenging for a classifier to see the difference for the training time hacking data. Okay, I think there are 3 things to take away. So the first one is that the prompted hacking data flatters your monitor, so it can score near 100% on prompted hacks and collapse to like only to chance on hacks that emerge during training. And the second is that we actually have a method to collect emergent hacking data at scale. And then the third is that we should evaluate our monitors on emergent behavior, not a prompted one. So if you rely on a monitor that is trained and test on the prompted one, its test set has to like contain hacks that the model produces on its own. And there are some limitation in future works for the talk. So one honest limitation is that the tracer covers only mostly evaluation process exploits. So by the mechanism of it, it only labels the hacking that try to pass the sweep by passing the contradictory the contradictory sweep. So our data is essentially like a clean subset of the reverse hacking. It doesn't mean to cover all of it. And another is that we only tested on small models. And we plan to, in the future, try traces on more complicated hacking beyond unit tests, and also on larger scale models. And we also plan to test it on more complicated environments like AGT long horizon settings. And also we are running experiments on co-evolving hacker monitor, so that the hacker and the monitor can evolve together and collect and labels newer hacking data. And that's everything I had today.